Okay, so good morning once again. My name is Tomasz Balon, and today I have the pleasure to present you the new thermal automotive dataset for object detection. And this paper was written under the supervision of Professor Bogusław Cyganek. Although there are many efficient deep learning methods, object detection and classification in visible spectrum have many limitations, especially in case of poor light conditions. To fill this gap, we created a novel thermal video database containing frames with annotated objects acquired in far infrared thermal spectrum. Thanks to this, we were able to show its usability in the traffic object recognition based on the YOLO V5 network, properly trained to gain maximal performance on thermal images, which contain many small objects and are characteristic of different properties than the visible spectrum counterparts. The proposed thermal database, as well as the fully trained model, are main contributions of this paper. And these are made available for free for other researchers, which will be shared later. Additionally, based on the highly efficient car detector, we show some sample application in the car speed measurement based exclusively on thermal images. The first part of the whole experiment was the data acquisition, and the data which provided with this article was collected using the thermal imaging camera FLIR A35. The whole acquisition took place in the afternoon before 3:30 p.m. to 4 p.m. The weather was cloudy and around -3 degrees Celsius. As you can see in the top right picture, this is our setup that we used to collect the data, and the bottom right picture is the RGB image of the field of view the setup had. It also depicts exact weather conditions and approximate time of the day. The next part was the annotation of the data set, and the short video on the left depicts some sample images which are taken from the data set. These images have either JPG or BMP format. They have low resolution, which is crucial to the data set, and they are in 8-bit grayscale. And the whole data set contains over 6,000 annotated images with more than 30,000 objects instances. Annotations are stored in the text files, also provided with the dataset that is supported by YOLO. Within the whole dataset, the four classes are annotated. As shown in table, these are person, car, bus, and truck, with most of them being cars. To maintain the consistency with COCO dataset, also as shown in the table, we use the same class IDs. Chart in the middle shows the distribution of instances over classes within the dataset, and the dataset, along with pre-trained YOLO model, is publicly available under the presented URL. After the annotation of the dataset of the images, the time for training has come, and this slide presents the results of training our model. It was trained for 50 epochs to observe if it would lead to overfitting, and the training metrics also presented on the right side, as we have the precision recall and average precision. Images on from top left to the middle show the predictions of labeled objects on validation dataset, and the image on the bottom shows the prediction of brand new unlabeled image, which wasn't seen by the model before. So after we did that part with training the model, we decided to have a sample exemplary application, which is speed measurement based exclusively on thermal images. The main idea behind this application is to show what possibilities do we have even in poor lighting conditions. We take into consideration two photos with time delta of exactly 1 second between taking of those two, which can be set by taking the timestamps provided with those images. let's also consider the car marked in yellow circle. To measure the vehicle speed, we need to have some reference in case of the distance traveled. And this can be done in several ways, but for our sample application, decided to use the line marks between the right and the middle lane, which are marked with red line on the bottom images. Based on the knowledge where the recordings took place and the standards according to which the stripes are painted, we concluded stripe and gap length. So now, knowing the exact time delta, space delta, which was between those two pictures, we can calculate the distance, the velocity of the vehicle, which is around 61 kilometers per hour. Although no radar data was acquired to back up this calculation, the result we have is believable and within the allowed speed limit on this road, which leads to the conclusion that velocity can be measured by calculating distance traveled within certain time-stamped frames, only basing on the thermal images. So future possible applications within the dataset presented in this paper can be used to develop computer vision systems for numerous applications like traffic monitoring, traffic management for smart cities, as well as surveillance and advanced driver assistance systems. Thanks to usage of long-wave infrared imaging, such systems will be immune to even the harshest lighting conditions, providing the same level of accuracy during day or night. The main contributions of this paper is the novel thermal imaging dataset with automotive scenes. It contains several thousand images with hand-annotated objects. Second contribution of this paper is trained object detector based on YOLO v5 architecture that shows high accuracy in small object detection alongside with the high speed of operation. Both the automotive thermal database as well as the pre-trained model are available for free, as said before, on shared URL. And moreover, we present some sample application of our model for car speed measurement based on thermal images. Clear advantages of such approach are also presented. And finally, in the future, we plan to further extend our database as well as develop more resilient trackers that can reliably operate in dense road conditions and with thermal images. So thank you very much for your attention. That was all from our side. And if there are any questions, I will be more than happy to try to answer them.
Thank you very much for a very compact presentation. So now it looks we have enough time for a few questions. So please ask the presenter if you have any questions. If not, I'll do my part. So I'll have two. The first question is regarding the acquisition scenario. You collected your data set, I understand, in winter time.
Yes, exactly. That was winter.
Yes. So to what extent do you believe the results can be, well, are applicable, are transferable to the same problem of detection of and possibly other things of vehicles in other weather or climatic conditions? For example, in hot summer in an Arab country, just to give an example. To what extent the thermal profiles could be similar, or even in Poland, but in a hot summer?
So, as mentioned before, the main advantage of infrared is that it's really robust when it comes to the weather conditions. Also, the car silhouette in the summer doesn't really change compared to the winter, but the main difference will be discovering the car on the road, which also will be warmer than in winter.
Exactly.
However, I suppose that the silhouette and the car itself can be visible. Also, there might be a need to pre-train our model for it to be able to catch and detect cars in the summer.
Yeah, exactly. What I believe, it should be trained not to recognize very hot road surfaces as accidentally as vehicles, because I believe that may happen. And the second question is regarding this speed measurement. So I understand that it requires some careful calibration of your system, because otherwise all these steps you propose will not work if we don't know exactly the distances you mentioned. Am I right?
Honestly speaking, we didn't really deep into that topic of calibration. It was just a sample application which we wanted to cover, but it's also the whole the application which we talked about is only like the field for future development, and is yet to be researched more and developed more. Also, as we said, it was only to be covered on thermal images without the radar, which also might be helpful in that application. However, for that particular one, we didn't really dive deep into the whole topic.
Yeah, thank you very much.